Okay, plus. Okay, we already done this. Yeah. Okay, so let's continue our nuclear discussion. Okay, so part one we learn about atomic Rutherford contribution. Then we stop at isotope. After isotope, that's it. Now the size of atom, size of nucleus, size of atom is how much? Negative 10. Size of nucleus is negative 15. Therefore, negative 15 or negative 15 or negative 14. Okay. Radioactive decay, as I said, who experienced that? Unstable nucleus. Why they become unstable? Because big proton number, repelling force, electrostatic force is stronger than the nuclear force, so decay happens. Okay, a radioactive nucleus is an unstable assembly of neutrons and protons. They can't stay together. Too many protons repel, so get stronger. Okay, neutron is do the neutron and proton as force between them? Yes, nuclear force. It's called nuclear force. Stability is achieved emitting ionizing particle and gamma rays. Yeah, stability is achieved releasing some energy from the nucleus, and radioactive decay make them to become stabilized. So of course, the type of particle after they emit alpha and beta particle, the nucleus composition become smaller. Maybe the proton number or the nuclear number gets smaller and become more stable. Okay, because alpha take away some proton and nuclear number. So nuclear emitting alpha beta particle change their identity to become a different element, which can also be unstable. Yeah, as I said, the daughter nucleus not always stable. They are slightly stable than the parent, but not completely stable. The process continues, okay, until ion, as I said. Okay, so again, periodic table, I think anything more than 85 proton number, as 85. It's around 85, more than 85, found to be the lower part here, all like unstable. Okay. Even smaller particle, you make it unstable by injecting neutron. Enter the neutron. This one nuclear bomb, right? Nuclear bomb, uranium. Uranium, what type of uranium they used? 235 nuclear number. Okay. But 235, okay. But when they insert a neutron inside, bombarding a neutron inside, become 236. 236 is very unstable. Okay. Suddenly a distance get further, they split. Okay, 236. Okay, now talk about stability. Okay, this is what the data has been collected. This is neutron number versus proton number. Okay, you know the zigzag line. The zigzag line is the line where the stable elements are lies. Okay, this straight line is n equals to p. N equals to p. So you see, for an element to be stable, they found through data they found that the neutron must be slightly bigger than the proton. Okay, you see, under 26 neutron with 82 of proton, it's stable. Okay, so neutron must be larger than proton with a certain number, it becomes stable. Okay. Okay, now if you have an element at this region, okay, you have an element at this region, so that means definitely it's unstable. It's unstable because it has excessive neutron or excessive proton. It has excessive neutron. So neutron need to be dropped so that it reaches this line. So excessive neutron. Okay. If it has excessive neutron, 1 0. Sorry. So what So what the nucleus must do? Must reduce the number of neutron. Must reduce the number of neutron, or can increase the number of proton, or increase the number of proton. Okay. You reduce the number of neutron, you fall here. If you increase the number of proton, you might reach here. Line. Correct. So normally what happened? The neutron, I don't know whether you remember, you realize, you heard about this or not. Neutron will convert to proton. Sorry, 1 1. Neutron will convert to proton. You heard of this before? Some of you maybe heard of that. Neutron can convert to proton. Yeah. And what will emit it? Beta negative. Beta is emitted. So 1 1. Yeah. So now it's balanced. Yeah. This happens here, this region. So this beta will be emitted plus another substance called, we will be discussing this. This is antineutrino. Antineutrino. Don't worry about this. Okay, we will be discussing this. For time being, what do you need to understand? Excessive neutron will convert to proton. Produce what? Beta negative. Beta negative. Okay. So any element on top here will release beta negative. Sorry, beta negative. Element which has excessive neutron, more chances to radiate beta negative. So try to decrease the number of neutron, increase the number of proton. Okay. Okay, let's say you have an element here, this region. This is also unstable, but this is due to excessive proton, lots of proton. So what the nucleus will do? The proton will convert to neutron. So can happen. Proton will convert to neutron, and what element will get here? 1. Sorry, this is 0. This will be positive 1 or negative 1. Positive 1, right? Proton number must be same. Positive 1. This is called positron, or in other words, beta positive will be emitted. Early studies, you never heard of beta positive. Now beta got two types: beta negative, beta positive. Beta negative is electron. Beta positive is something called positron. Positron element, subatomic particle, same as electron, but only different is charge is positive.
So positron or anti-electron?
Yeah.
Positron or anti-electron?
Normally we call positron. Okay. So this is happens for what? Excessive proton. You have lots of proton. The nucleus got a lot of proton. So you reduce the proton, increase the neutron. If you have element which is at here, this is what? Excessive neutron, excessive proton, both very high. Okay, so what you should do? Try to reduce both. So how you can reduce both? By releasing alpha. Okay, by releasing alpha, you reduce the neutron and proton both. Correct? Like for example, uranium convert to something else, a new substance. Let's say A plus helium. Yeah, helium 4 2. So the new substance, let's say this is this is 235. This is 85. I'm not mistaken. Let's say 85, 235, 85. So the new element form will be 234, 231. Sorry, 231. Down will be 83. So release of alpha reduces the nucleon number by 4, reduces the proton number by 2. So it reduces the neutron and proton. Keep it. will be alpha. Okay. So yeah, this is what happening every time. So anything far away from this what you call stable line, they will emit radiation, achieve stability. What type of radiation they achieve depend what is excessive with them. Neutron excessive, beta negative. Proton excessive, beta positive. Both excessive, alpha. Okay. Okay, so let's proceed. Okay, types of decays. So we know three common types of radioactive decay: alpha, beta, and gamma. Okay, emission of beta can be further divided into beta minus and beta plus. Gamma never change the composition of the proton and neutron inside the nucleus, but gamma always won't appear alone. Gamma always accompanied by alpha or beta. After alpha release, then gamma will be released after that. Okay, after beta release, gamma might be released, but not only gamma release, never happen. Okay. Okay. Yeah. So you know this alpha decay reduces the proton number by 2, neutron number by 2. So an example, yes. So uranium changed to thorium, so 1 alpha comes up. The thorium more stable than uranium because its neutron and proton occupants has been reduced. Okay. So this is the equation supposed to be, right? Whenever they say decay, the helium must be a product. Decay. Okay. This equation in exam, they won't ask you to write, but sometimes they make the numbers empty, fill up the numbers. That's easy, right? Check the nuclear number, both sides must be the same. But you need to know the formula for few substances. You need to know the formula for proton, neutron, electron, and helium. What are the nucleon and proton number? Proton is what? 1, 1. This you have to remember. Neutron is 1, 0. Electron is helium. This you have to remember. This they won't tell you. You have to know. Okay. This power you have to remember. Other than that, they will give you. Yeah. Oh, gamma. Just the symbol. If only gamma comes out, just write here plus just gamma with 0, 0. No proton, no neutron number. You never put 0, 0 also fine. So just gamma symbol. Okay. So beta minus, when that happen, excessive neutron. Excessive neutron, beta minus happen. So when the nucleus is too many neutrons, the neutrons decay into protons by emitting a beta minus particle. Number of neutrons in the daughter nucleus decreases by 1, number of proton increases by 1. Nuclear number remains the same. Yeah. So you see, thorium become the protactium. So what happened? The proton number increased by 1. Nuclear number drops. Neutron drops by 1. This equation. So beta, you can put E or you can put B, beta sign. Okay. the sign. This is antineutrino. Beta always form antineutrino. We will discuss this. In real exam, you must put antineutrino. Okay, this 0, 0, right? You put it in front. No need to put at the back. Put in front. 0, 0. Okay, antineutrino. Okay. From 5, maybe you just write beta accepted. A-level beta plus antineutrino must be written. You never write antineutrino, you lose mark. Okay. Why that antineutrino happens, we will be discussing later. Okay, beta plus excessive what? Proton. Excessive proton decays into neutron by emitting beta plus, called positron, fast moving positron. Number of proton and daughter nucleus decreases by 1, number of neutron increase by 1. So proton change to neutron. The number remains. This is what happens. Again, yeah. When beta plus release, the type of element comes out, put the 0 at the side, is neutrino. This is called neutrino. If beta negative 1, then it will be antineutrino. We put a bar. Antineutrino. Neutrino, antineutrino. Beta plus, neutrino. Beta negative, antineutrino. You heard of matter, antimatter? Antimatter. Okay. What is so special about antimatter? According to scientists, what they said, mass can convert to energy, energy can convert to mass. Okay. Let's say energy form mass, and the energy create mass is always create equal amount of matter and antimatter. Okay, equal amount of matter and antimatter. Like, yeah, matter and antimatter. So you won't only get matter alone. You'll get matter and also will have a antimatter. Okay, and the matter and antimatter meets up. What happened? It tend to become energy again. You saw the movie Star Trek. Long movie. Star Trek, you know, the Enterprise. What type of fuel they use? Matter, antimatter. One side matter, another side is antimatter. Matter, antimatter was allowed to react, produces the energy to move forward. It's a futuristic movie. Currently, we don't have any. We don't have antimatter. Okay.
I thought we can make, but it's very, very
unstable,
expensive.
Yes.
1 gram is
most expensive. If you have 1 gram of antimatter in your hand, means you are the most richest man in the world. 1 gram of antimatter, what is the price? I think few trillion. The price, 1 gram of antimatter. Check from the net how much. 1 gram of antimatter, what is how much the value? 1 gram of antimatter. ANTI matter, antimatter. How many gram? How much?
62.5 trillion.
60?
$62.5 trillion.
$62.5 trillion. You are all top richest people are billionaires, not yet even 1 trillionaires. Okay. So yeah, antimatter. So when energy convert to matter, it becomes matter and antimatter. So what I'm trying to tell you this story is about the beta and neutrino. Okay. You see, first one, the first one is beta. The second one, beta negative. Beta negative is matter. This is matter. Electron is matter. Okay. You know the positron? Positron is antimatter. Positron is antimatter. You see one reaction, for the first reaction, antimatter is formed. Antimatter is there, beta positive. So the neutrino is the matter, neutrino is matter. Neutrino is matter, antineutrino is antimatter. Any nuclear reaction, you will have matter and antimatter will form. Okay. So that's why beta is matter, you will get antineutrino, antimatter. Okay. Beta always antimatter. Beta always together with antimatter. Positron, beta positive always with matter, neutrino. Okay. That's why they say existence of neutrino, okay, was proved. Any matter must have an antimatter, must appear together. Okay. Currently, all we have is matter. We don't have antimatter. Okay. But when the universe is when the 13.7 billion before, when the universe is with energy and everything, they do have matter and antimatter. But whenever the matter and antimatter meets, they change to energy. So what happened? They were like a fuel, or they burn. Finally, what happened? Only matter is here. That means, and originally matter is more, antimatter is more. Coincidentally, matter looks like more. Okay, originally, matter is more than antimatter. The one left is, let's say matter, maybe I put a number like 10 and antimatter maybe 8. Now we only have 2 matter. The one remaining matter. Okay, so why I'm explaining this about the neutrino? Matter must have, antimatter comes up, and the nuclear reaction happens. Okay, so yeah, let me clear this. Okay, so neutrino, the presence of third particle neutrino and antineutrino were initially introduced by conservation of momentum. I told you the movement. The third one they found is they should have another third particle, and matter and antimatter theory. They say later they found it's neutrino. Okay, scientists says few billion neutrino now passing through your body in a second. Okay, from the sun. Okay, and the speed of neutrino is found to be speed of light. But recent studies, someone saying that some scientists predicted the speed is of neutrino is exceeds speed of light. Okay, but not proven yet. If it's proven, then all the Einstein's idea is collapse. Okay, his idea is all based on speed of light, never exceeds speed of light. Okay, beta decay later on. We're going to. Okay, gamma decay, a nucleus excited state will emit gamma ray. Excited state means nucleus has lots of energy levels. When alpha, after release alpha, it will be in an excited state, high energy level. After a short while, the energy of the nucleus will drop down, releases gamma. Okay. Gamma are packet of electromagnetic radiation of discrete energies. It's gamma is a type of EM radiation. Discrete energies we will do in depth in A2 later. For time being, for AS, you say it's a EM radiation, will do. Okay. Of course, you never change the composition of the proton and neutron number. Frequently followed beta decay or alpha decay. It accompanies beta or alpha decay. After beta done, then gamma might happen. Okay. So, yeah. Okay, so this is 24094, 24094. Composition never changed, but the energy level of the nucleus is dropped. The energy was released as gamma. Okay. Okay, as I said, this is the flow of the radiation. The partial line up to lead. Lead, after lead can lead to the another part. They say no need to go for iron. We're most probably going to stop at lead because its half-life is big. Consider quite stable lead. So every time uranium change to thorium, I think you can check what type of radiation is keep on releases. Keep on releases until they reach the lead. Yeah. Okay, so now we're going to talk about, I think early studies you've done, right? The difference between alpha, beta, and gamma. You have to know. So just recall back. I think you've done this before. So alpha is what? It's made of 2 proton, 2 neutron, or to be one shot, what is it? It's a helium nucleus. It's a helium nucleus, made of helium nucleus. Don't ever say helium atom, wrong. Helium nucleus. Beta is of course electron, high speed electron, and beta plus also is high speed positron. Gamma is EM radiation, no charge. Okay, rest mass for alpha is 4u, 4u. Beta minus is u, beta plus also u, 1u. Or last time we just take 4, 1, 1, but actually it's 4u, 1u, 1u. U at the back, you need to multiply by 1.66 and 10.19 to get mass in kilogram. Okay, this is called rest mass. Okay, why the word rest came up? Again, because of Einstein. What is meant by rest mass? It means an Usain Bolt not moving, his weight may be 70 kilogram. And Usain Bolt run forward, its mass rises. Sounds funny, huh? When someone running fast, he gets fatter. Idea of Einstein. You never seen that, right? Anyone gain kinetic energy, the particle gain mass, according to Einstein and the theory of relativity. Okay, looks funny, but later indirectly has been proven. How they prove? They prove the electric field. Electric field. Use electric field. You learn about electric field. Yes. Electric field. They put a, let's say, electron. They accelerate the electron. And they accelerate the electron. What happened to the electron? Electron gain kinetic energy, right? So they want to see what voltage you apply exceeds speed of light for the electron. Okay, so half mv squared equals to what? What is work done by the field? What formula? What times what? QV, right? QV. So half mv squared equals to QV. So half mv squared, they put the V as the speed of light for the electron, mass of electron. They found the voltage. What voltage? So after they calculate the voltage, they apply that voltage. They accelerate the electron. Electron never reach speed of light. Never ever reach speed of light. They increase more voltage than that. It never reach speed of light. So that means, what's wrong in that formula? Kinetic energy has been gained, but work done equals to half mv squared. So there is some mystery happening. It works for a low voltage, but it never works for close to speed of light. So later, theory of relativity law, the mass rises. The mass for the electron, it seems, rises until to infinite and get close to speed of light. So nobody can attain speed of light. Okay, because the amount of energy required to attain speed of light, half mv squared, the m become infinite. So the kinetic energy the person must possess is infinite. So we can't supply that energy. So his idea was working in the theory. Okay. So that's why the term rest mass was introduced. Okay. When the helium electron, when they are rest, not moving, this is the mass. Okay. For human, rest mass, I don't think so it's applicable. You run with 10 meters per second, the most we can do, Usain Bolt, let's say 10 meters per second. Its mass won't rise that much. Okay, it mass only has a significant big change when you move close to speed of light. Even when close to speed of light, a lot of funny things happens. Mass rises, time runs in a different speed. All in under his theory of relativity was revealed. Okay, so rest mass. Speed of helium is only 10% of speed of light. Speed of electron is almost speed of light, 99%. And gamma, of course, is speed of light. Okay. And ionizing power. What is meant by ionizing? What is meant by ionizing? A process where a neutral atom loses electron. Become ionized. Alpha has the greatest ionization power. Why? Anyone? Yes? Yeah, why? Because it's heavy. It can do lots of collision before come to rest. So ionization is smaller. They say more collision. So it can ionize the air up to 10 to the power of 4 particles. Okay, before you come to stop, alpha particle. Beta particle is 10 to the power of 2 and gamma is the lowest. Okay. So ionization is a factor which is quite dangerous for us. Very high ionizing means cancer. Very easily can happen. Okay. So good news is alpha very ionizing, but what is the good news? Yeah, its range is short, only a few centimeters, less than 10 centimeters. Okay, you have a source of alpha radiation here. Further than 10 centimeter, you are safe. Or you put a piece of paper to block, it stops. Okay, but let's say if it's exposed to your hand, for example, like you are someone, some you know, the what you call radiation lab in universities. Radiation lab, the technicians are very vulnerable for radiation. They ended with a lot of radioactive substance. Let's say they use their bare hand to touch uranium, whatever radioactive substance, and unfortunately they have a small dust sticking in their hand. Let's say they inhale it, and it stays in their lungs. Let's say a small one dust of uranium, okay, get into your lungs. What is the half-life of uranium? It's 500 over years. Okay, I think more than that. So the lung, permanently the uranium will stay in the lung. So what happened? You're going to radiate alpha, beta, gamma. Alpha is there definitely. So definitely going to get lung cancer. Okay, maybe in 1 year, depending on how strong is your immune system, but you will get. Okay, so that's why alpha, very high ionization power. Although it's a short range, but if you inhale it, big problem. Okay, let's say a nuclear bomb blast happened in somewhere like that. What is the only nuclear most famous incident? Chernobyl. Chernobyl, when the dust, tons of dust exposed to the atmosphere. Not only that country is affected, the neighboring countries. Anyone inhaling that dust, they might get cancer. Okay, that's why every country is against the nuclear bomb. Okay, so penetration, yes, one paper for alpha, beta is a few millimeter aluminium, a sheet of aluminium required, and gamma is a block of lead. You know this, deflection, electric field and magnetic field. Alpha deflects slightly. Why? Very massive, although charge is greater. And gamma is the greatest deflection, and no deflection for gamma because no charge. Okay, so remember these facts again. Okay. Okay, penetration, as I said, piece of paper will do for alpha, beta is sheet, and gamma is a block of lead or 10-meter concrete wall. Okay. Okay. So effect of electric field, the deflection, sometimes they ask you to draw. Okay. So beta deflect the most, and alpha deflect little, gamma goes straight. Electric field. Okay. Effect of magnetic field. How do you find the direction of deflection? By using Fleming left-hand rule. Okay. Alpha is deflect down. The magnetic field, the magnetic field is out of the page. Dot is out of the page. Yeah, dot is out of the page. Out of the page. Yeah, out of the page. Yeah. Then FBI, right? F is force. Your thumb is force. Your index finger is what? Magnetic field strength direction. Your middle finger is your current. Okay. So P is out of the page. Current is for the alpha is to that direction. Okay. And force should be downwards. So drag down. Okay, right. Correct. FBI. Okay. So current follow the direction of the positive charge particle or negative charge particle movement. Positive charge. So alpha moving to the left means current is to the left. Direction of the current. Beta move to the right means current is to the opposite direction. Okay, Fleming left-hand rule. Don't use right-hand rule. Left. Okay. Yeah, magnetic field entirely in A2. So we'll be discussing this one. Good to know this Fleming rule. Not even once in asked in AS, but yeah, good to know. Okay, radiative decay. Okay, now this is the radiative decay has a two nature. It's spontaneous and it's random. The process is spontaneous process and random. What is meant by spontaneous? Spontaneous. It's not affected by external factors. Pressure, temperature, now can't control the radiation. And when a blast happens, nuclear, the radiation will be there. Can you control it? You can't control it with any mode. You can't increase the pressure or decreasing the temperature. It won't change. Is it a good or bad for human? For us, it's bad because we can't control it. Okay, so out of control. Once the explosion happens, the radiation level will be there for a long time. Depend to the half-life of the substance. So spontaneous, unaffected by external factors such as pressure and temperature. Okay, second, the process is random. What is meant by random? Unpredictable. We don't know. You have a 1 kg of uranium. We don't know which atom going to turn to radiate. Maybe sometimes inside atom, sometimes outside atom. Sometimes 10,000, sometimes none. Totally random, unpredictable. It's not possible to predict which and when unstable nucleus will decay next. However, there is a constant probability for a nucleus decay in certain time interval. The keyword is the first line. We don't know which and when an unstable nucleus will decay. It's totally unpredictable. Okay. Next, okay. This one pass here. On here they show these two graphs, T1, T2. T1 is the lower temperature, T2 is the higher temperature. They ask which feature of the graph tells spontaneous nature of the process. Which nature of the graph tells random nature of the process? Which appearance of the graph tells is a spontaneous nature? For T1 and T2, for different temperature, the shape of the graph remains the same. For different temperature, the shape of the graph remains same. Okay, and the experiment is carried out. The higher the temperature, the same best fit line is obtained. Yeah, same best fit line is obtained. Therefore, is spontaneous. Okay, unaffected by temperature, external factor. And which tells the random nature, the fluctuation of the reading. The fluctuation of the reading. The zigzag lines or the fluctuation of the count rate reading for both graph tells the random nature of the process. That means last time your form 5 you learn, right? And time 0, the number of activity, let's say C, after exactly at half-life, the value must be half C, right? But in reality, when you do the experiment, at half-life, the reading could be a little higher than half C or could be a little lower than half C. Depends. First time you repeat, maybe a little more than half C. You repeat again, it will be a little lower than half C. So, but it's about that value. But the reading is always fluctuates, shows random nature. Okay, not exactly that amount of nucleus will disintegrate at that time. Sometimes can be lower, sometimes can be higher. Okay. It's random. Okay. Okay, class. So that's about alpha, beta, and gamma. Okay. Let's answer for this. So gamma is EM radiation and beta is high-speed electron. Okay, come on, give me this answer. Find the equation. That means 2 beta. 2 beta. So which element will be produced? So it emits 2 beta. Oh no, it absorbs slow neutron. It subsequently emits 2 beta. So write the equation. How the equation looks like? The uranium 238 92. It absorbs slow neutron. That means it absorbs 1 neutron. Neutron must be the reactant. It absorbs what? Forms a new element. Is what we are looking for. The number here. And releases how many beta? 2 beta particle. So 2 beta was released. So this is your equation. So what is the number on top and bottom should be? So this round should be 94, right? Oh yeah, 94. 2 times -2. 94 minus -2 is 92. Top should be what? 2381. Then should be 2391. So C is the answer. Okay. So write the equation. Absorb, bombard. A neutron was bombarded with uranium. Neutron is reactant or product? Bombarded. Should be reactant. Decay helium. Decay alpha. That means alpha is product.
We assume that it's just beta negative.
This is the old path here. The beta negative, beta positive came into the syllabus 2017, I think. So when it comes after 2017, all what beta plus beta negative. 2016 passes all, we just put beta because we only learned beta negative 2016. Now they should place. Okay. But if they never see, currently also never place, benefit of doubt, they take it as beta negative. Beta negative. Okay, yeah, this one. Answer. Emission of beta particle. So beta negative. Beta negative, excessive proton, excessive neutron. Beta negative, excessive neutron. So neutron going to drop, proton going to rise. So proton is increases, nucleon number unchanged. One proton change to one neutron change to proton, so nucleon number unchanged. One says proton number is increased, increased and unchanged. So D now, answer is D. This one emission of beta particle by emission of alpha particle. Okay, write the equation and fast give me the answer. 30 seconds. So decays by emission of beta particle. Emission of beta particle. So beta particle reactant or product is the product. Beta particle is product followed by emission of alpha. So alpha also product. Both of them product. What is the nuclide shown is formed? So 241 Pu 94. So it's never bombarded with anything. It just emit a new substance plus with 1 beta, 0 -1 and 1 alpha for 2. So what is the value here should be 239. Yeah, so this should be 239. Down here is 93. Yes. So 239 93. Yeah, so A is the answer. Yeah. So try to learn how to write the equations. Which is it reactant or product? You have to check. Decay, product. emit, product. Bombard with neutron, neutron is reactant. Okay. Okay, last one, last for today. Education. First is beta particle, then alpha, then beta particle. Beta particle, neutron change to proton number, I guess. Alpha drops the proton number. Okay, so which statement is correct? P release beta become Q. Q release alpha become R. R release beta back become S. P and S are identical in all respect. True? I think the alpha are going to change the nuclear number. So I don't think so. So what's the answer? P and S as isotopes of the same element. P and S, are they same isotope? Yes. The proton number is same. Correct? So the proton number, let's say here 20. After beta, proton going to drop or rise? Rise by 1, 21. Then alpha means the proton number going to drop by 2, going to become how much? 19. Then beta again rise to 20. So they are isotopes. P and S is isotope. Yeah. So the answer is B. S has a different element of low atomic number. S different element of reduced mass. Same elements, both of them same elements, they are isotopes. Okay. So I stop here. So you do your reading later. Next going to be something new. We go to the core, proton made of what? Okay. We're going to come to a particle zoo. We thought only 3 particles inside the nucleus, and the scientists did experiment. They found 200 over particles inside the nucleus. Okay, but in your syllabus, we only talk about few, not all. Still under research, not proven yet. Okay, we stop here.